welcome everybody to another session of the seminar. This time we have Logan Crew with a graph polynomial for chromatic symmetric functions. Logan Crew comes from the University of Waterloo. He is a research assistant there, a research professor assistant there, and he obtained his PhD in 2020 from the University of Pennsylvania. He works mainly with symmetric functions and with chromatic symmetric functions and many symmetric functions arriving from graphs. So let's welcome him and thank you for being in this seminar.
Thank you so much, Diego. Thank you everyone for coming here. And this is joint work from an undergraduate research project in this last summer with William Chan at Waterloo. And I'm looking forward to seeing how he does because this was a great project and he did really great work with this. So we're going to start with the basic definitions here, just so we're on the same page. An n-coloring of a graph G is going to be a mapping from the vertices of G to the positive integers 1 up through n, such that whenever you have an edge in G, its endpoints get different colors. So to be clear in this talk, I'm going to be dropping the word proper, and a coloring is just going to refer to a proper coloring. Although, of course, I kept that phrase in on this slide here, but that's okay. The chromatic polynomial is the unique function such that chi g of n is the number of proper n-colorings of G. And the chromatic polynomial was originally constructed in part to study the four-color theorem. And in doing so, Birkhoff and others after him have found and popularized the deletion contraction formula, that if you have an edge in a graph G, and you take it and delete that edge, and you subtract the chromatic polynomial from when you contract that edge, you get the same function. So let's briefly go through an example of how that actually works here with deletion contraction. And so, for example, if we have this graph, we're going to show it in this form using this bottom equation, that the chromatic polynomial of G delete an edge is equal to that on G plus G contract an edge. And you do this by simply bijecting the proper colorings. So here's a proper 3 coloring of a graph. And this is the edge in question that is deleted up here. If you have a proper 3 coloring such that its endpoints get different colors, then it is also still proper in the graph with the edge inside of it. And there is no meaningful way to make it proper in the graph with the edge contracted. Note, by the way, that when you contract an edge, as you see going from here to here, you take the vertices and identify them at the endpoints. You generally keep multi-edges if there were multiple edges from some vertex to one or more of the endpoints. For the purposes of this talk, that doesn't matter so much because multi-edges don't affect chromatic polynomials or chromatic symmetric functions, but for Tuttled polynomials or symmetric functions it will, so I will generally keep them in the illustrations anyway. So this is the case where these two endpoints get different colors. Well, what if they get the same color? If they get the same color, then, well, we're going to have this issue where this is not a proper coloring of this graph over here, but we can identify to a proper coloring over here by simply giving that color to this shared endpoint that we contracted to, and it's pretty clear how that bijectively works. And so we have a bijection between proper 3 colorings, in this case, of this graph up here, with that of one of either of the other two, and that would establish this identity. It's very simple, classic counting argument, but it's really nice, and it allows you to do a lot of things inductively with the chromatic polynomial. You can prove a lot of properties by direct expansion or by induction on the number of edges, and it makes things work out very, very nicely. So here, for example, is a theorem of Whitney's from 1932 that the chromatic polynomial could be represented as a sum over the edge set, and this is perhaps best illustrated with an example. Let me briefly draw that here. So if, for example, I wanted to give you the chromatic polynomial of a graph with these three vertices and these two edges, then I'm going to sum over all subsets of the edge set. In this case, there are 4 possible subsets of the edge set because there are 2 edges. If I take none of the edges, then the number of edges I've used here is 0, so I get a positive sign, and I get into the number of connected components. In this case, that's 3. There are 3 distinct vertices. If I take exactly one of the edges, there are 2 ways I can do that. And in both cases, I am getting 2 distinct connected components. And I get a minus sign because I'm taking an odd number of edges. And in the last case, I am taking both edges. This again gets a positive sign, and there is only 1 connected component. So that is how you could determine that the chromatic polynomial of this graph is in fact n cubed minus 2n squared plus n. And for what it's worth, this is the first direct place where I have shown you that this is indeed always a polynomial by definition. And how do we prove this? I mean, we kind of just go through what I did here. You apply deletion contraction to all edges of G. In this case, I didn't explicitly contract the edges I'm keeping in, but you can, right? If I had contracted this edge here, in, for example, this case where I kept 1 edge, I would contract it to a thing with 2 vertices here, and the chromatic polynomial of a graph with just k vertices is pretty clearly into the k because I can color each of those vertices independently. And that is why this basically corresponds to this. You get a sum of that number of terms corresponding to contracting the edges that you keep and deleting all of the others. And so that is how that proof is basically going to work here. We also have a more recent theorem of, for example, Stanley's in 1973, where he showed that the chromatic polynomial also gives you the number of acyclic orientations of a graph as an evaluation, oddly enough, of chi-g at -1. It's really weird when you think about it for a second. Obviously, we defined this polynomial initially for chi-g of n being proper n-colorings. It is not at all obvious that there should be a reason that evaluating it at a negative integer should yield anything interesting. But up to this predictable sign, it tells you the number of acyclic orientations, and in fact, more generally, chi-g of -n tells you the number of ordered pairs of acyclic orientations and weak n-colorings, where weak means it is equal or increasing along the orientation. I won't go through this full proof here, but the proof sketches, this is where we could use the inductive style of proof. For graphs with no edges, it is easy to check that we have an empty orientation on the edges as the only orientation, and this works out. And in between, if we are going to delete and contract an edge E, basically we show that the number of acyclic orientations works across. There's 2 basic cases. If we have a directed path between the endpoints, then there's only 1 possible orientation for E and not the other. And if there's no such directed path, then we're going to end up counting a couple of different orientations, but the mathematics the arithmetic property is going to work out there. So the chromatic polynomial contains some surprising information sometimes. And that is why, in part, we want to generalize it to a symmetric function. There are lots of reasons to generalize it to a symmetric function. And let's just go ahead and do that. So for the chromatic symmetric function, we're going to be using a function with a countable number of variables, x1 up through x2, etc., infinitely many of these. We're going to sum over the proper colorings of the graph, but instead of counting each proper coloring just once, and in defect counting it by the number of distinct color it uses, we're actually going to give it this monomial. What does this monomial tell us? It tells us that if we use, for example, 2 vertices that give the color 2, then we're going to get an x2 squared. So what is that telling me here? It tells me that, for example, if I end up with a term x1 squared x2 squared x3, that I have 5 vertices, and that I've used the color 1 twice, and the color 2 twice, and the color 3 once. This is more information, of course, right, than just that it uses 3 colors, but it tells me the distribution at which I use these colors. That distribution could be different for using 5 total colors on 5 vertices. And that's the added information that this gives us. Now, formally, this function is going to be a power series over, it doesn't super matter what the coefficient ring is, as long as it's a field of characteristic 0 containing the rationals for our purposes. I'll just say R. It is a symmetric function because if I was to permute the variables, I would get back the same function. Why is that? Because if I take a proper coloring of a graph and I permute the colors, that's still a proper coloring. Just simply permuting the stable sets does this, and so it's easy to check that this is going to work out. And for what it's worth, this is clearly a actual specialization in the sense that if I were to take this particular case where I set the first n variables equal to 1, then what's happening up here, well, every term that uses only colors from 1 up through n is going to get counted once. And if it uses colors from outside of that, it's going to get counted 0. So in fact, this just sums over all proper colorings that use only the first n positive integers and counts each of them once, which is by definition chi g of n. So this does properly contain this up to a substitution of finitely many non-zero entries. I might take a brief second here and to pause and ask if anyone has any questions up until this point. And if not, I will continue in a second. Okay. So as we were saying, for example, these are the different kinds of colorings you could get. If I'm coloring this graph using 3 distinct colors, then here's an example where I'm getting this x1 cubed, x2, x3 term, and symmetrically from all of these other permutations. Some other things with this exponent pattern of 3, 1, 1. And here is an example where I'm getting a pattern of 2, 2, 1. And for those wondering what this graph is, this is a graph from a while ago that I created from Delta Airlines flight paths between cities, which I conveniently named X Delta because I'm funny like that. So what my wife Sophie Spurkle and I did in our original paper on this general subject in 2020 was we were thinking about this and we were like, this doesn't have a deletion contraction relation, not in a simple sense, right? Because the issue here is that if I was to contract a vertex, what's going to happen? What's going to happen is that the number of vertices obviously decreases, but that's a problem because our exponent pattern, its sum depends on that number of vertices. As soon as I contract and I try to take a chromatic symmetric function, I have something whose total degree is lower. So xg and xg delete would both have degree 5 in this case, but xg contract would have degree 4. Clearly, there's no easy way to make a deletion contraction relation that's going to make that work. Now, to be clear, there are various ways you can make it work. Oriana and Scott, for example, did develop a triangular modular relation that sticks entirely within this, and that's fine. Other people have done things with non-commuting variables and other various ways you can make something like a deletion contraction relation. But in our case, we wanted just to find something that's the most close to the original and that most directly admits for similar arguments to the chromatic polynomial. So that is why we extend this vertex, this graph definition to include a vertex weight function where the vertices might be weighted. If we do this, then we just have the same definition, except that when we count these variables like x2, its total exponent is not going to be the number of vertices that get color 2, but the total sum of the weights of all of the vertices that get color 2. If we do that, then we do get a deletion contraction relation, and in fact, it's kind of the obvious one. All we have to do is modify it so that when we contract an edge, when we add the vertex weights of the endpoints. And that is what's going to recover that missing degree factor in the thing. So for example here, suppose we have this graph where, to be clear, the colors represent the, well, colors, and the weights are represented by the positive integers. So these numbers are the weights, they are not the colors. And we have the same exact proof as I showed you before, right? So this would be a monomial, for example. This is what, something like x1 to the 5th, x2 cubed, x3. And if we are looking at this graph, then since the endpoints of this edge got different colors, we have the exact same coloring in the original graph, and that's fine, and it's going to give us the same monomial. And on the other hand, if we go down to here, where the endpoints have the same color, well, here we had this x1 to the 5th coming from two vertices of weights 3 and 2, and when we contract them, we add the total weights and we get a weight of 5. And so that x1 to the 5th is in fact preserved, and the two monomials coming from these colorings are indeed the same. And so the proof then follows precisely like the other proof, with just this minor modification of adding the weights when we contract. I would also give a shout out here to a paper by Joel S. Monaghan and Ian Moffat. And they and others have written a series of papers about a function called the V polynomial, which is an extension of this where basically, roughly speaking, the vertex weights are generalized. The vertex weights can come from basically any algebraic object where you can add weights and it's still in the thing. I think it's technically called a torsion-free abelian monoid or something. I don't know exactly what the detail is, but basically where you can give each vertex a weight and you can add the weights and it's still in the thing. And that's all you really need. You don't even need inverses to the weights particularly, right? You just need to be able to add them. And it was partly through Joel S. Monaghan contacting me and telling me about the V polynomial that we found even more results on this. So I just wanted to give a shout out here to that. So what is going on with symmetric functions? Let's briefly summarize a little bit of the actual algebraic properties of symmetric functions as we're going. An integer partition of a positive integer n is going to be a sequence of positive integers that we write in non-increasing order. So equivalently, we're writing a set of positive integers. And in this case, I forgot to omit the n, but for example, if we want to partition the integer 8 into different integers, then we could, as a set, partition it into the equation 8 is equal to 4 plus 2 plus 1 plus 1. And since it's a set of positive integers, to most simply write it, we just write it using this convention that we write it as a sequence, but it's in non-increasing order. And where is this coming into play? To go into a little bit of the technical details here, as we saw earlier, the actual monomials that we are getting out of this chromatic symmetric function basically fundamentally depend on this exponent pattern. So we're going to define a function m lambda tilde, and I'll explain the tilde, is summed over all monomials that used these distinct colors, I1 up through ik, and where lambda is of length k, and we give them these exponents in order. Now, as a brief note, this is strictly speaking, a multiple of m lambda because we are getting multiplicities based on the exponents. For example, if I have an x1 squared, x2 squared, let's see, I guess the short answer is that basically the issue is that under this definition I am saying here, this is the same as x2 squared, x1 squared, and I do want that. This monomial should have a coefficient of 2, x1 squared, x2 squared, if I were expanding m22 tilde. So to be clear, this is off from the usual definition by the multiplicities factorial. Basically, there's 2 copies of 2, and so I could reorder them like this. The same is going to be true whenever we have multiple exponents of the same value. And why do I want that? I define it this way precisely so that this fact holds. That m lambda tilde is in fact actually just the chromatic symmetric function of a graph with these vertex weights. So for example, by this definition, m tilde 3, 1, 1 is in fact just the chromatic symmetric function of the complete graph with vertices of weights 3, 3, 1, and 1. And the original theorem of Stanley for unweighted graphs that we slightly modified for our case, basically you can boil it down to the m lambda base tilde counts the stable partitions of the graph partitions into stable sets. And this makes sense, right? When we look at a proper coloring of a graph, the color classes induce this set of stable partitions. And this lambda of pi here being the integer partition, whose parts are the weights, in our case, of the blocks of pi. Well, that's just coming from when we have an x1 to the 5th, we have total weight 5 of the things that get color 1, and that must be a stable set of weight 5. So this is pretty easy to see. And what other good bases are there of symmetric functions? One good example is the p-basis. The p-basis is usually defined as p sub n is the sum of all variables to the nth power, and you'll note that under our definition, that is the chromatic symmetric function of a single variable of weight n. And likewise, p lambda is defined by being multiplicative across its parts, and this is just going to be the chromatic symmetric function of the complement of a complete graph, just those k disjoint vertices of those weights. And with this in mind, we can see that this theorem also generalizes. So you might remember the similar thing we saw for the chromatic polynomial. This is the same basic thing. We're summing over all subsets of the edge set. We have -1 to the number of edges, but now we get this more refined thing where instead of just counting each connected component once, we actually will also reserve the weight of that connected component. And this follows from the exact same proof, right? If we delete and contract every edge, except now we have our vertices of weights 3, 2, and 1. Well, if, for example, we only keep this edge and we contract it, then we're ending up with a vertex of weight 5 and a vertex of weight 1. So instead of getting an n squared, we're getting a p5, 1. We retain those weights. And in particular then, to pass to the chromatic polynomial from this weighted thing, another way we could view this is by mapping each power sum function p sub k to the variable n. We can do this because the pi are algebraically independent of each other in our context. And so this is a perfectly fine way to map this to the polynomial. And I will be entirely honest with you, I don't know all of the details of exactly how formally all of the algebra in this talk is from the point of view of formality, but I'm mainly using this more as a motivating factor in any case. So if anyone does find things that they think are issues, feel free to point that out. And one other basis that we have, the elementary symmetric function basis, where En is defined to be the sum of all sets of distinct positive integers, basically monomials of degree n, where each variable has degree 1. So in particular, E4, for example, is going to be represented by just a clique of weight 4, right? Because then these have to all get distinct colors. We divide by n factorial because right now we would get 4 factorial copies of coloring it with the variables 1 up through 4, because the vertices can get the colors in any order. And E lambda is just multiplicative, and that just means that it's going to be this multiplicative product of these disjoint unions of cliques. Stanley discovered a very intriguing theorem, which is one way to state it is define a polynomial by mapping E sub k to the variable n. then what Stanley says is that the coefficients of this polynomial count the acyclic orientations of G and striate them by number of sinks, meaning vertices with no outgoing edges, directed wise. This is somehow very weird and unexpected, right? It was already a bit weird that chi of -1 gives us the number of acyclic orientations, and somehow it's even weirder that the E basis in the chromatic symmetric function gives us even more detailed information. It allows us to count them by number of sinks. I will say, I am not talking about this in this talk, but there is a proof in the original paper of myself and Sperkel that we do generalize this theorem to the vertex weighted case. It is not quite as pretty as simply doing the substitution, which is why I'm not going to talk about it here, but there is at least an extension to the vertex weighted case that basically ends up with a signed sum over certain pairs of acyclic orientations and other things. So anyway, this means that we can get a lot of graph polynomials nicely from the chromatic symmetric function. And here's the point in the talk we've all been waiting for, getting to where the title is. We've seen the chromatic polynomial and this acyclic orientation polynomial, which by itself is perhaps not often studied in graph theory by itself, but it does come from this. Another thing we can do is we can count matchings in the graph, right? If we think about what's going on with P2, it's possible that when I wrote this, I might need to be a bit careful about signs. Maybe this would be like the absolute value of the matching polynomial. I would need to figure this out. But the short answer is that you can, basically, if we have a matching in a graph, well, what that actually induces in the connected component sense is a P2 to the 3, 1 to the in -6 or whatever, basically, right? In terms of we only keep some of the edges and we delete all of the others. And these P's, as this number varies, is going to tell us how many distinct matchings there are in the graph. So I think possibly what I've written here is wrong and I need to put in a sign. Maybe it's P2 to the -n or something like that. Or maybe it's not a direct substitution. But in any case, basically, if we take P2 to n and P1 to 1 and the other Pi's to 0, then we're getting rid of all of the terms that are kind of dumb here and that don't tell us anything about matchings. Everything that's left with P2 and P1 is going to tell us about how many matchings there are. So we can recover the matching polynomial from some sort of simple substitution. But the main thing I'm going to talk about involves the tree polynomial of a graph, which is, as far as I'm aware, a newly defined polynomial by myself and Chan. And in order to talk about the tree polynomial, we need to talk a bit more about expanding graphs into bases from symmetric functions. We've already seen how you can represent the P, the E, and the M bases, traditional bases of symmetric functions, but you could actually express them as chromatic symmetric functions of vertex-weighted graphs in a nice way. And in fact, the basis expansion formulas for these things could naturally arise from just applying deletion contraction repeatedly in a nice way. You can always reduce to a complete graphs or to the complements of those by deleting contracting. Deleting contracting will get you to P's, and doing uncontraction will get you to M's. It's a bit less obvious as to how you could get to E's from this. And honestly, in fact, if we could do this, that might tell us more about the E basis, but I suspect in principle it is possible. But more generally, what if we want to expand this in terms of any set of graphs that's sufficiently nice, basically? Not just the family of complete graphs or the family of empty graphs. Well, this is where we can use some theorems here. An original one for unweighted graphs by Cho and Van Willigenburg, and I will use this abbreviation throughout for a more recent paper of Alaneafard, Wong, and Van Willigenburg. Where basically they say, when can we do this for a family of graphs? Let's take, and the answer is basically any time the graphs are nice in the obvious sense. We clearly need graphs to be connected. If they're not connected, then they factor as a product. But if we have a family of connected graphs, one for each positive integer, and where gi has total weight I, then in fact their chromatic symmetric functions are algebraically independent. We kind of would hope this would be true, and it's not hard to show it is true, but it is nonetheless nice for it to be written down very simply that this is in fact true. So if we define this notation xg lambda by, well, it's the product of xg across, or in other words, you could view it as the single chromatic symmetric function of the disjoint union of g sub the parts, then we do in fact get unique expressions of this form where we can expand one chromatic symmetric function over this family. And so in the specific case where we pick the g's to be single vertices of weight n, we recover the p basis. When we choose it to be these complete graphs with weights prescribed by lambda, that doesn't immediately obviously follow from this because that's kind of the complement here, where we're, instead of doing disjoint unions, we're doing complete joins. But it's basically the same idea, and it's not hard to show that that still works. And the same is true for the e-basis. That does directly come from this. I might stop here for a brief moment and ask if anyone has any questions.
The total weight is the sum of the weights.
So gi has total weight I. Yes, that means it's the sum of the weights of the vertices.
Okay. And you mean algebraically independent? Actually, you mean that they generate the ring of symmetric functions?
Yes.
Okay. And freely. Okay, thanks.
Yes. Yes, it's a very nice fact, and it's, at the same time, it's kind of obvious this should be true, and also it takes a bit of effort to actually prove, but basically once the p-basis or the m-basis, well, the p-basis especially is pretty easy to see it's algebraically independent when you have a nice ring going on in infinite variables, and then the rest kind of follows from an upper triangular matrix argument, basically. So we're going to define this tree polynomial. So we've already talked about this chi f of x. Basically, we're going to be a bit more formal here and take this from the point of view of letting chi f to be defined for any symmetric function f by letting each pk be specialized to the variable in question. So that by what we've said before, if we have a vertex-weighted graph, then chi of the symmetric function is actually just chi g in the traditional sense of the chromatic polynomial. So basically this chi f is a generalization of the chromatic polynomial of a graph to any symmetric function. And here's where we're going to work with trees. Now here's an important point here. We are going to ask that our trees each have I vertices, not total weight I. There's going to be a technical reason for this. But basically, suppose that we have our vertex-weighted chromatic symmetric function, and we do write it in this function, in this tree basis, which we know we're allowed to do by the previous lemmas. If we apply our chi function to each side, on the left-hand side, we're going to get chi g. On the right-hand side, chi is going to distribute across these various trees. Now, what exactly is chi of t lambda? Chi of t lambda is going to be, well, if it's a tree with, if we have a tree with I vertices, it's going to get chromatic polynomial x minus 1 to the rest of the variables. So if we have a disjoint union of length of lambda trees, we're getting x to the length of lambda, x minus 1 to the rest. Here is the point where we do require it to have I vertices, not because this equation doesn't work per se, but because we do want to be able to collect them nicely like this. Now, what's the important fact here? The important fact here is that if we collect like terms, then the sum of these a lambdas for a fixed length is going to correspond to this. And it's not hard to check that these are independent as polynomials, as length of lambda varies for a fixed number of vertices. In particular, that means that this a lambda is independent of the actual choice of the trees, because we started with this any choice of trees, but we are always going to end up with this because every tree has the same chromatic polynomial. And so we can define that expand xgw in any tree basis where we require each ti to have I vertices, and the polynomial we get is independent of the choice of tree because of the chromatic polynomial being indistinguishable on trees of a given number of vertices. We can define this function to be the tree polynomial of our vertex-weighted graph. So this is the definition of the tree polynomial. It makes enough sense that we want to try to deal with this. Now, why is it going to end up being nice? Why did we study this in the first place is a fair question. One of the theorems of Alefeyenard, Wang, and Van Willigenberg is, in particular, among other things, they showed if you have a path of n vertices defined by Pn, then if you look at the asymmetric function endomorphism that maps Pn, the power sum in function, to the chromatic symmetric function of the path of n vertices, this is an involution. This is a very nice fact. This is a very nice fact that is going to be a lot of what allows us to relate the tree polynomial to the chromatic polynomial. And how are we going to do that? This is going to be a slightly technical part, and I'm going to I'm going to be vague on the details here, but the short answer is how are we going to compute nice things about the tree polynomial? Let's say that we have xg written in the p basis. Then by definition, we are going to calculate the coefficient of x to the k in the tree polynomial by this sum. So we can just sum over this path basis. We can pick any set of trees, right? Any set of trees to determine the coefficients of the tree polynomial. So we might as well pick paths because they're nice to work with. And then we are just going to rewrite this by expanding xg into the p basis. So we have our sum over lambda of a lambda. We have a sum over delta of this fixed length for the x to the k, then this coefficient of the path delta in the p lambda function. Now the critical point we need here is that this involution tells us that this coefficient is the same if we swap these. And this coefficient is the same if we take the coefficient of p delta and xp lambda. This very simple point is quite nice because xp lambda is nice. Because in fact, what are we going to be doing here? If we have xp lambda, then, so what's p lambda again? Let's remember, it is a set of paths, one up through length of lambda of them. And we want the p delta coefficient of this, where delta is something that has length k. We also are then going to want to look at what's the length of lambda. Let's say the length of lambda is m. Since we're summing over all of these partitions, all of the p lambda that have length k, basically what we're saying is we have here length of lambda components, and we want to have length of delta components. So in particular, we just need to delete some edges. Here we have n minus length of lambda edges. And we need to delete enough of these edges so that we have exactly m components. It's not hard to check that then this number that we need is going to be length of lambda minus m, basically, because then we're going to get n minus m edges and m components. I might have slightly misspoke as I was going through this, but this is kind of the short answer is now, if we're computing the coefficient of p delta and xp lambda, this is just a straightforward calculation, especially since we're summing over all of them for any fixed lambda and for any delta that has a fixed length. So basically the short answer here is we're going to get this sum. We're going to get this -1 that is signed appropriately based on the number of edges we're doing in the p expansion. And this is the number of ways to reduce that path function into some p lambda, p delta that has that fixed length of parts. And here we are going to do this by summing over the different lengths. So this is a slightly tedious calculation I don't want to spend too much time on since I need to go on to other things, but I think you can hopefully roughly believe that this is true. And so we're going to simplify this by summing things out, refactoring. And then we notice that what's this here? Well, remember what A lambda was. It just came from the P basis. And remember, the P basis turns into the chromatic polynomial. The sum of these coefficients is in fact just this coefficient of x to the m and chi g. So what have we shown here? That the coefficient of x to the k in our tree polynomial is in fact represented by some combinatorial formula on the coefficients of the chromatic polynomial. This fact is slightly gross by itself, perhaps, in the sense that this formula isn't super nice, but it is what will allow us to show that the tree polynomial has some nice things because the chromatic polynomial does. So for example, let us compare some interesting properties of these. In chi g, well, if you take chi g on a weighted graph, you get back chi g. It doesn't tell you anything about weights, which kind of makes sense by the definition. It's about colorings and the edges between them. It says nothing about the weights. Tau g, on the other hand, does tell you something about the weights. Tau g does tell you what is the excess weight of the function in the sense of the graph, in the sense that it tells you the total weight of the graph, the sum of all the vertex weights minus the number of vertices. So how much more weight it has than 1 per vertex. And you can tell this exactly because you can show that tau g, when g is unweighted, does not have x minus 1 dividing it. So in fact, this excess weight is exactly the power of x minus 1 that divides tau gw. On the other hand, we know that the leading coefficient, for example, of chi g is x to the number of vertices. But for a tree, tau t is x no matter how many vertices the tree has. So the chromatic polynomial tells you how many vertices the tree has. Tau does not know this. Tau knows the excess weight, but it does not actually know how many vertices there are. So somehow between the two of these functions, chi loses all information about the weight, but knows exactly how many vertices there are. Tau knows relatively how much extra weight the graph has, but not how big it is. And so somehow between the two of them, they kind of can combine to carry a lot of this information. They do both have a deletion contraction relation. From the chi g and from the calculations we just showed, it is possible to show that tau g does also admit a deletion contraction relation, where this x minus 1 factor is coming from in part. It does also have this clique product and quotient, in the sense that if g is formed as an intersection of two graphs at a clique, then you could compute its chromatic polynomial as that of this times this divided by that of the single point. And the tree polynomial tau actually does have the exact same property, and you can verify that passing through the details. One other thing that's of some interest, we can pass between the two of these not just through the coefficients, but it is possible to do something slightly different, where if I know tau g, and I do actually know the exact total weight, so I do need this extra information that I need to know the weight of the graph and therefore the number of vertices if I know tau g already, then chi g I can find by taking x minus 1 to the weight and substituting x over x minus 1 into tau. And conversely, in the paper this comes from, you can find that basically the same formula reciprocated allows you to solve for tau g in terms of chi g, if you know this additional information about how much weight the graph has. So in particular, if you're always working with unweighted graphs, then this is perfectly fine, and you can recover chi g and tau g from each other, which makes sense. I find this particular fact fascinating, and we didn't particularly use this for a lot, but the fact that they have this reciprocal relation in terms of fractional evaluations seems interesting to me, at least. Now, I've gone through comparing tau g to chi g. It certainly seems to have some suggestive properties, which I like. But what else can we do with this? We know chi g is the number of proper n-colorings of g overall. Does tau g have a nice, simple interpretation in terms of what its evaluations are? And we also want to know what its coefficients are. So I'm going to go through this part slightly quickly since we are running a bit lower on time. But given a graph G, this is where we're going to use some tut-like this stuff here. and we are going to be looking at the broken circuit complex of a graph. So we're going to order the edges of our graph arbitrarily. It will not matter because the edge ordering is going to be independent of these results. So a broken circuit of G is a cycle minus its smallest edge. So if we have a cycle labeled like this, then this would be a broken circuit, for example. I see somebody had a question. Is the involution on lambda that sends P in to xtn defined over the integers? I do not know the details on that. That you would probably have to check the paper of Thanoid, Wong, and Van Willigenberg to check the details on that. I don't know if that's defined over the integers or not. It might be because that kind of comes from just a deletion contraction-y style argument that should be preserved there. I'm not sure. And so the broken circuit complex of a graph then is going to consist of all of these edge sets that contain no broken circuits. Elements of this circuit complex we are going to call internal forests. Do note that implicitly this is internal spanning forests. And if you're familiar with the terminology, you'll recognize internal here is a nod here to internal and external spanning trees of the Tut style formulation, although we don't need those exact details here. And maximal elements of BG we are going to call internal spanning trees. We're going to use this notation even if G is disconnected. And so if G is disconnected, we will still call it a spanning tree if it's an edge set that consists of if it's an edge set that consists of a spanning tree for each component, we will still call that a spanning tree for our purposes. And why do we care about this? And I see in the chat, I think we have figured out that the involution on lambda that sends Pn to xPn is not defined over the integers. So that's a fun fact. I didn't know that. And so what Whitney showed is that edge cancellation thing, summing over all subsets of the edge set. Actually, we don't need to use all of the subsets of the edge set. It suffices to look only at these sets of the edge subset that contain no broken circuits, right? Basically, the short answer is everything else is going to cancel out somehow. Everything that has, for one thing, cycles in it, somehow cycles, you can cancel out terms because you can remove edges from the cycle and it cancels the term. Basically, this is saying, let's just put an ordering to the edge set and let's cancel cycles by canceling it with removing the smallest edge of the cycle. Obviously, there's some more detail to it than that, but that's kind of the basic idea of why we're doing this, is to reduce this to simplest terms. And this is cancellation free because for each of these forests, this exponent in the sign depends on its number of connected components. So there cannot be any cancellation among the summation terms here. And what does that have to do with us here? I will try to get through this last bit a little quickly. If I have a spanning tree of a connected graph and an edge not in the tree, then I am going to call the fundamental cycle of the graph to be the unique cycle added when we put it in. So here's a spanning tree of this graph, and here's an edge. Its fundamental cycle is going to be this cycle. What we discovered, Chan and I, is that there's a couple of ways you can interpret these coefficients of the tree polynomial. One way you could choose to do it is you could count the number of pairs e comma t, where e is any set of edges. We will label them e1 up through em for some m. That is a k cut set. So this is where the actual k comes in, is how many components the edge bed splits us into. And T is an internal spanning tree of G, so that for every edge in our tree that is one of the edges from our chosen set, there is some smaller edge that is not in the tree, and such that EJ is in its fundamental cycle. This is a weird statement, in some sense, but it does give us an explicit combinatorial interpretation of the coefficients of the tree polynomial in terms of simply counting certain things on the graph. And since we're running low on time, I'm going to kind of skim through this proof, but to put it simply, first of all, we have this formula that I'm just copying from the other page here. One thing we can do here is we can now use our definition that we used on the broken circuit complex and write everything in terms of that. In particular, what we have here when we do x to the coefficient of x to the m is we are choosing we're choosing a forest, right? We're choosing a internal forest that has this coefficient. And when we do n minus m choose k minus m, we are choosing a subset of its edges, meaning that we are choosing a subforest of it that has k edges. So one way we could view this is summing over all elements of the broken circuit complex with length k, summing over everything that is bigger than it of length m, because we're summing, this should be a k1 to m, I think. No, that's right. And we are taking -1 to its length. That comes from the -1 to the number of edges from above. And again, I'm going to skim through the details of this arithmetic calculation. But this is a sum ranging over internal forests with k parts and b an internal forest that it contains a. We are basically going to map a to its set of cut edges. So a is a forest in the graph. We are going to map a to the set of edges that connect to distinct blocks of A. This is invertible, and this means that we can now work in terms of these edge cut sets. So for a choice of a fixed k-cut set of edges, we are summing over all internal forests that contain, in our particular case, it's going to be b minus e as a subforest. Now b, of course, might not contain all edges of e, that's fine, just b minus whichever edges are in it. So let us call this S not the set of those B that are internal forests that work like this. Let's put this to page. Basically, the short answer is we're going to inductively create sets. And I want to take a couple minutes to go over this, since I do think this is interesting. Basically, we are going to have those B that are internal forests that lie above our given set of edges. We also want to, in order, have them satisfy the second property above this particular property in terms of internal spanning trees and being in fundamental cycle of a smaller edge, if the edge is in our element. And if not, then we want this to contain a cycle. Why is that? Because basically at the end, we're going to end up with only internal spanning trees remaining. Right now, we're using all forests. And at the end of its internal spanning trees only remaining, then this is automatically going to be satisfied anyway. And we can check that detail. So basically for the in-between steps, we're going to force that to be true. The trick here is that ST plus 1 can be formed from ST actually by just removing pairs of elements that cancel in the sum, so that the sum remains constant as we shrink the set that we're summing over. In particular, if we look at any particular internal forest in ST, so that if we unify it with t plus 1, so we're only looking at those that don't contain et plus 1, and if it doesn't contain a cycle, we remove it, and we remove its corresponding element as well that does contain et plus 1. There's a lot of details to be checked here, that we do have to remove these elements in order to satisfy these conditions, that elements that should still be in play are not removed, that everything is still maximal. But ultimately that all will work. There are basically details of checking that, for example, if we are going to put in et plus 1, and if it would be valid because it was in the fundamental cycle of a smaller EQ, then basically what if we would put it in, and then what happened when we put in EQ? When we put in EQ, it passed this thing and was still in the set only if this did not contain a cycle, right? Basically, the issue is that when we added it here, it must have contained a cycle. But then here's a cycle that contains et plus 1. So I'm sorry, this logic is... Basically, the short answer is we show that it has to be this way, that when we add this thing, if et plus 1 is valid, then things work. And there's a lot of arguments of this sort in this proof. We can show that each SI is maximal with this property. And once we get to the final edge, the final SM, basically, if it were not maximally connected, then any edge that would be outside of it would be one of these EIs, which would be a contradiction. And so, in fact, each of these SMs is, in fact, an internal spanning tree. And so this whole sum cancels as we pass from S0 to SM because we remove elements in pairs. And so we end up with this final statement, which is exactly this. And here's the -1 to the k, here's the -1 to the connected components, and this sum is equivalent to the statement that's up there, the number of internal spanning trees that satisfy all of these properties. I can give everyone a second to look at this, and then I've got like 3 more slides, and then I'll be done. Does anyone have any questions? And if people have questions about this proof, I can come back to it later as well. Using a similar idea, by the way, we can show that from our direct calculations earlier, this is one way to write tau g of x also, is in terms of coefficients of the chromatic polynomial in this way. But we just stated that this is the up to assign the number of internal forests with k components. And if that's true, then this is just the chromatic polynomial of those components. And so what we immediately get is that one way we can write tau g is that up to a sign it sums over all properly n-colored internal forests of G, summed with alternating sign based on their number of components. Which is itself an interesting little combinatorial interpretation for the output of tau G, which we didn't define it this way because why would we, but it comes from this. And basically, we can do the same argument we did before of removing pairs from sums and transferring upward to show that basically we can actually reduce it to k-colored internal forests with stronger properties if we wanted to. That the endpoints of the smallest edge receive the same color and that it has these other properties. I won't go into the details of this now. We tried to do this in part because we wanted to see if we could reduce it from internal forest to internal spanning trees. Unfortunately, it does not in this form. Currently, we have internal forests and colorings that satisfy these properties, but we cannot guarantee it reduces to spanning trees as it does in the other theorem. But perhaps this is still a starting point for building from there. Basically, this theorem is just saying that we're again reducing the set of internal, properly k-colored internal forests to something stronger with more properties. So further directions going forward. As I mentioned, we would love to improve that basic combinatorial interpretation of the output to involve only properly colored internal spanning trees if possible. It seems like there could be a natural way to interpret this in terms of the lattice of contractions. There are nice ways to do this for the chromatic polynomial and chromatic symmetric function. And we did make some progress on that, but didn't really manage to reduce it to anything that was sufficiently simple. The fact that we have this interpretation of tau g as a signed sum over properly colored internal forests is interesting considering that it comes from chi g of x over x minus 1. I tried looking up what I could about fractional evaluations of the chromatic polynomial, and I know that these substitutions do something to the polynomial, but somehow that intrigues me, that in principle, this means that there's some meaning to certain fractional evaluations. And ultimately, we were trying to work on the tree isomorphism conjecture, namely the conjecture that trees are distinguished by the chromatic symmetric function. It's almost a laughable conjecture, given that the chromatic polynomial, completely doesn't distinguish trees in any way whatsoever other than number of vertices. And yet, as far as we can tell, it seems like this might be true. It's true up to 29 vertices, last I've checked. So why would this be true? I'm not entirely sure, but it might be. And this is kind of where we were hoping to go with this. This work comes from this paper, A Graph Polynomial from Chromatic Symmetric Functions by myself and William Chan. It's on the archive. And thank you so much for coming.
Yeah, thank you for the presentation. Are there any questions on the chat, or yeah, in general? Yeah.
May I ask a question?
Yes.
It is just a small. You have a relation between your two polynomials chi and tau with
Yes.
your fraction inside, and
Yes.
it reminds me something like
Seconds on it.
Platism. Perhaps it's just a vague idea. Yes, this relation. Perhaps you have, since you are talking about symmetric polynomials also, perhaps there is some relation with Platism. I don't know.
I've wondered that as well. It certainly looks like a
Yes.
Platistic style relation, doesn't it? To be entirely honest, the short answer is I just ran out of time on this project before we got to the point where we thought too much about Platism, and then I went into other things. But I do agree with you. I could see where there could be something there. And I would love it if that were true.
Okay.
Thank you. I appreciate that.
Yeah. Thank you. Are there more questions? Yeah. It was. I have a question, which is more general. Yeah. When you were presenting about the cyclic orientations on, yeah, well, when you're presenting the chromatic polynomial, the chromatic symmetric function, and you explained that it has something to do with cyclic orientations.
Yes.
Do you think there is a direct way, or do you know if there is a direct way to include these acyclic orientations directly into the quasi-symmetric functions? Not in the symmetric functions, but in the quasi-symmetric functions.
I mean, so there is a chromatic quasi-symmetric function defined by, let me get to a place where I have some more.
I think Sharishan and Wax, maybe?
Yes, the Sharishan and Wax paper. So that's where they originally defined the chromatic quasi-symmetric function on digraphs. So formally they define it on graphs that are labeled by positive integers, although you could also in principle define it for a directed graph in much the same way. And basically the answer is that you give it proper colorings, but you also give it a factor of q to the number of ascents in the coloring, where ascent means that the colors increase along the arrows. Or if you're labeling it with positive integers instead, the colors increase along, the colors increase when the vertex labels increase. So doing this with vertex labels is essentially equivalent to doing this on an acyclic graph. So there is a direct definition on digraphs, and it is true that there are some things on chromatic symmetric functions that you can express as a sum over always to acyclically orient it. And then doing combinatorics on quasi-symmetric order posets on the acyclically oriented thing. Stanley showed some results in his original 95 paper, for example, in this way, by passing things to posets that correspond to acyclically oriented acyclic orientations on the graph. So there's a couple of ways that you can bring in acyclic orientations in a quasi-symmetric way. Stanley does it by kind of splitting the chromatic symmetric function into certain quasi-symmetric functions. Shresian and Walks go the other way, where they generalize the whole thing to a quasi-symmetric function that implicitly has something to do with orientations.
Mhm.
So those would kind of be the two obvious directions I could think of.
Yeah. Okay. Thank you on that. Okay, I will check then on this article. There are more questions on the chat or in the public, from the public, because I just have another question quickly. So what was the conclusion, or what was your comment about whether or not you can reconstruct the two-te polynomial from these three polynomial and the chromatic polynomial? Like, do you think you can reconstruct one from these two?
My guess would be probably not. I mean, so keep in mind they're equivalent on unweighted graphs, right? The chromatic polynomial and tree polynomial are in principle equivalent on unweighted graphs, and that you can recover one from the other. So certainly you could not combine those to get the tut polynomial.
Yeah, but like
So,
I was thinking that when you are using the lesion contraction, you are taking this information into the weights.
yes.
So probably, yeah, probably you can use that. But okay, yeah,
No, I
probably
see
not.
what you mean though. Yeah, I guess if you,
Yeah.
I don't know exactly. My educated guess is I still suspect that there might be some issues there and that I'm not sure, but then again, they are dual in a nice way, like the tut polynomial has some inherent duality, so I don't know exactly. That's an interesting question.
Yeah, but that was exactly my question, because this duality you mentioned. But okay, thank you for the talk. It was very nice. Thank you for the public, and I'm not sure if we are going to have this post discussion in Gathertown. Can somebody tell me if we are going to have that?
No, it's not. No,
Okay.
I don't think.
Okay. So we shall thank again to our speaker, and that's for today.
Thanks for having me.